Since July, the world has been watching 3I Atlas speed through our solar system. But in October, just as this now infamous interstellar object started to get close enough and bright enough to Earth to study properly, our view of it was blocked by something else, rather close and far brighter: our Sun. The ground-based telescopes that had been tracking its every move for months were now blinded at a most frustrating time. We'd just begun to study its strange molecular ratios, saw it change color twice, and even spotted a strange and unusual sunward tail that some suggested might be evidence of artificial propulsion. Meanwhile, subjected to the sun's intense radiation and moving at a staggering 68 kilometers per second, it wasn't clear if 3I Atlas would even survive the journey around our star. But all was not lost. Out in space, a fleet of probes, telescopes, and even Mars rovers were keeping a keen eye on 3I Atlas as it dived towards perihelion. Would it make it out the other side, disintegrate in the sun's searing heat, or would it do something else completely unexpected? I'm Alex McColgan, and you're watching Astrum. Join me as we dissect the stunning new data from 3I Atlas's Mars flyby, find out what happened behind the sun, and analyze the smoking gun evidence from a South African radio telescope that could settle the debate about whether we are looking at a volatile comet or something that is intelligently navigating the dark. Before 3I Atlas even vanished behind the sun, it gave us a warning that it was no ordinary comet. In late August and September, NASA used their SWIFT observatory to watch 3I Atlas as it approached the sun. SWIFT is designed to spot gamma-ray bursts, but its UV capabilities allowed it to see things invisible to the human eye. In this case, the glow of hydroxyl, or OH, radicals. These molecules are the broken fragments of water, ripped apart by sunlight. And what SWIFT detected was a massive surge in those hydroxyl radicals. At a distance of 2.9 astronomical units, nearly 3 times the distance from Earth to the Sun, 3I Atlas was dumping water at a rate of 40 kilograms per second. To put that in perspective, that's the output of a fire hose running at full blast. For a comet this far out, where temperatures are still freezing, this was shocking. Standard models suggest water ice shouldn't sublimate this aggressively until it gets closer to the sun. This fire hose behavior hinted that 3I Atlas wasn't just sublimating water from its surface, it was likely ejecting icy grains into its coma, which were then melting independently, vastly increasing the surface area. But before we could find out more, this comet dipped behind the sun and disappeared. Throughout October 2025, Earth-based telescopes had to take a break from watching 3I Atlas. This was the worst possible scenario for astronomers. The most exciting moment of the comet's journey was happening on the opposite side of the sun from us. When warmed by the sun's radiation, it would be at its brightest and would be outgassing violently. But while Earth may have been blind, we already have plenty of probes and telescopes in the deeper reaches of the solar system, some of which were perfectly positioned to watch the show as the comet made its closest approach to the sun. A new study led by Qicheng Chang from the Lowell Observatory in Arizona and Carl Battams from the US Naval Research Laboratory aggregated data from 3 specific spacecraft: Stereo A, SOHO, and the newly launched GOES-19 satellite. These 3 spacecraft use chronographs to block out the sun's disk, creating an artificial eclipse. Usually they hunt for solar storms, but in October, they were hunting a comet, and what they saw was a metamorphosis. For months, as 3I Atlas approached the inner solar system, its brightness had been steadily increasing. Astronomers measure the rate at which that brightness increases as a power of an object's distance from the sun, or R. Before October, 3i Atlas's brightness was increasing at a rate of roughly r to the minus 3.8. That is a respectable rate for a comet, indicating active sublimation of material from its nucleus. However, inside 2 astronomical units, the brightness slope didn't just steepen, it went almost vertical. The new data shows a brightness scaling of r to the minus 7.5. That's a huge increase. The comet was shedding mass at a rate that defied standard models for a simple dirty snowball. It was bright enough that, by the time it emerged from behind the sun, even amateur astronomers were able to image it from Earth. These are some of the images taken of 3i Atlas during this time. In them you can clearly see a bright coma streaking out behind the comet. Although the core of 3i Atlas itself is a little harder to make out, they were taken by astrophotographer Paul Craggs, who used a Dwarf 3 smart telescope from Dwarf Lab, a telescope I've been trying out myself recently, as they've kindly sponsored this video. I like this telescope a lot. It's really proficient at this kind of deep sky imaging. Its live stacking helps it build up clear and detailed deep sky images in just a few minutes, especially impressive for such a compact smart telescope. It was really easy to set up. Once I got it on its stand, it quickly oriented itself using the stars, so it was simple for me to point it at the stars and comets I wanted to image. I also liked its portability, as I didn't want to be lugging around a heavy telescope on a cold winter night. But the Dwarf 3 is light and easy enough to use that I didn't have to worry about that. Although the best window for imaging 3i Atlas has already passed, if you're looking for a very good value smart telescope to help you take images of other beautiful birth of a solar system moments, from nebulae to star clusters and any future comets that might be coming past, then try this one out. Scan my QR code or use the link below, then use my code ASTROM5 at checkout to get 5% off. The most telling detail about this newly brightened comet though was the color. For months, observers saw 3i Atlas as red, typical of dusty, organic-rich surfaces like those on Oumuamua. Then, it turned green to observers on Earth, as I mentioned in my last video on this comet. But the solar observatories saw something different. Through the filters of LASCO and Core 1 coronagraphs, Chang and Bottoms reported that 3i Atlas appeared distinctly blue relative to the Sun. A blue hue in a cometary coma is the signature of specific gas emissions, fluorescence from carbon monoxide, and amide radicals. It suggests that, as 3i Atlas plunged towards perihelion, it shed its dusty red outer cloak. The intense solar heat penetrated that protective layer and began boiling off volatile ices from deep inside the comet. The real comet, the blue, violently outgassing engine inside, only revealed itself when it got close enough to the Sun. But these solar probes weren't the only ones watching. Just before the solar encounter, 3i Atlas paid a visit to our little red neighbor, passing just 0.19 astronomical units, or about 28 million kilometers from Mars. This was a cosmic stroke of luck, offering a unique opportunity for the fleet of robots currently exploring the red planet to observe. NASA's Mars Reconnaissance Orbiter swiveled its HiRISE camera toward the visitor. Now, HiRISE is powerful enough to spot a coffee table on the Martian surface from its orbit of 200 to 400 kilometers above. If anything was going to be able to get a resolved picture of the nucleus, it was this camera. But the US government shutdown affected many of NASA's departments, meaning it took weeks for the pictures to be published. The long wait to get a hold of these images sparked conspiracy theories that NASA had seen something unusual, perhaps extraterrestrial in origin, and were withholding it from the public eye. The images finally released by NASA nearly 6 weeks later were underwhelming. They show a fuzzy, unresolved blob. Even from this distance, the nucleus was hidden deep within a shroud of gas and dust measuring 1,500 kilometers across. Although we didn't get a beautiful, pristine photo of our interstellar visitor, at the very least, this non-detection may help scientists pinpoint how large 3i Atlas really is. but we already know from observations made by the Hubble Space Telescope that it is likely no more than 2.8 kilometers wide. But MRO wasn't alone. ESA were busy imaging 3i Atlas with Mars Express and the ExoMars orbiter, and NASA's MAVEN orbiter used this ultraviolet spectrograph to image the comet's hydrogen envelope, revealing a massive cloud of gas extending far beyond the visible coma. Perhaps most incredibly, the Perseverance rover, sitting in Jezero crater, fresh from discovering what might be evidence of life on Mars, pointed its mast cam skyward. In the resulting long exposure images, 3i Atlas appears as a faint, ghostly smudge drifting among the stars. These images may not look like much, but they are truly groundbreaking. This is the first time we have ever imaged an interstellar object from the surface of another world. And then, it was the moment we've all been waiting for: perihelion. As 3i Atlas emerged from behind the sun in November, panic spread through the astronomical community. Harvard astrophysicist and avid 3i Atlas commentator, Professor Avi Loeb, suggested that the comet had fragmented, that it had exploded into 16 pieces. It looked like our chance to observe this rare interstellar visitor might be over for good. His hypothesis was fueled by calculations suggesting the comet's mass loss was unsustainable. With the brightness surging so intensely, some models predicted the nucleus must have disintegrated to provide that much surface area for sublimation. However, new observations from the Lowell Observatory and the Virtual Telescope project have calmed these fears. Astronomer Zhang reported that the comet appears perfectly normal and healthy. There is no train of fragments, no chaotic debris cloud. The nucleus survived. The explosion was simply an intense period of activity, a natural fireworks show driven by the shedding of that outer crust. So, the comet is in one piece, but those who have been following the story of 3i Atlas over the last few months will not be surprised to find out why Avi Loeb was so concerned that it had fragmented. Over the last few months, Loeb had published a series of articles on Medium arguing that the comet's behavior exhibits anomalies consistent with extraterrestrial technology. Specifically, Loeb points to two features: a sunward jet appearing in images and what he describes as non-gravitational acceleration that keeps the object on a remarkably straight trajectory. Loeb argues that the mass loss required to produce such acceleration by natural outgassing would be immense, potentially enough to disintegrate the object. He suggests that if the gas cloud isn't massive enough to account for the thrust, we must consider artificial propulsion. As fun as this is to think about, and perhaps even to hope is true, in this case unfortunately, standard cometary science offers robust natural explanations for these phenomena. First, the sunward jet. Normally we expect comets to have a tail, or trail of gas and dust expelled from the comet, pushed behind it by the solar wind. 3i Atlas, however, appears to have a second tail in the opposite direction, facing towards the sun instead of away from it. Images from the 2-meter twin telescope in Spain's Canary Islands, taken on the 2nd of August but first released in October, show this jet close up. This image, a composite of 159 exposures lasting 50 seconds each, shows 3i Atlas as a big black dot in the center of a white glow. But the break in this glowing ring shows a jet of material blasting off the comet in the direction of the sun. Now, while this might look like a thruster firing against the direction of motion, this sunward jet is a reasonably common feature in comets. As a comet approaches the sun, the side of the comet facing it will heat up faster. If there's a weak spot on the surface, sublimating gases can then shoot out of the comet towards the sun. The solar wind pushes this material back, creating a fan or spiral structure that, from Earth's perspective, can look like a forward-facing spike. So this is not an unusual thing to see. In fact, similar features were observed on Comet Halley, Neowise, and Comet 67P. Second, let's address the non-gravitational acceleration. This is the rocket effect caused by outgassing and is a standard feature of all active comets. A new dynamical study by Goldie Ahuja and Shashikaran Ganesh modeled 3I Atlas's trajectory over the last 100 years. They found that its acceleration was entirely consistent with the fire hose, water loss, and the massive CO2 release we've observed. The comet is losing mass rapidly, just as Loeb calculated it would need to, but the survival of the nucleus suggests it is dense and structurally sound, not that it is artificial. Furthermore, the straight line trajectory Loeb mentions is largely a matter of perspective and reference frames. In a hyperbolic orbit, the object travels fast enough that gravity bends its path less than a captured object, making it appear straighter, but it is still following the predictable laws of Kepler and Newton. While Loeb's hypothesis serves a valuable purpose by pushing us to question our assumptions, the current weight of evidence, the chemical identification of cyanides, water, and that massive carbon dioxide load strongly supports the theory that 3I Atlas is a natural object. And the Meerkat radio telescope array in South Africa has now effectively ended the debate. Meerkat detected a faint but distinct signal at 1665 and 1667 MHz. This is an absorption line of the hydroxyl radical. We mentioned hydroxyl earlier with the Swift telescope, but this new radio detection is crucial. Radio waves can penetrate the thickest dust clouds, giving us a direct look at the gas density. The detection confirms the presence of water, and lots of it. This is the first time we've detected radio emissions from an interstellar object. It confirms that 3I Atlas is chemically similar to the comets in our own solar system. It is a wet, icy body venting water vapor as it heats up. If it were a dry, rocky spaceship or a defunct probe, this signal simply wouldn't exist. This effectively seals the deal. 3I Atlas is made of water and carbon, the building blocks of nature, not some exotic extraterrestrial alloy. So much for the alien spaceship theory. This object is undeniably a comet, but that doesn't mean it's not surprising us in other ways. One of the biggest assumptions we make about interstellar objects like 3I Atlas is that they are pristine. We imagine them as perfectly preserved time capsules, unchanged since the birth of their parent star systems. But a new paper by Romain Maggiolo from the Royal Belgian Institute for Space Aeronomy and his colleagues challenges this idea entirely. In fact, it suggests that we have been looking at interstellar objects all wrong. 3I Atlas, they argue, is not pristine, it is cooked. The evidence comes from the chemistry revealed by observations from the James Webb Space Telescope and the Sphere X mission, which detected an extreme abundance of carbon dioxide. In typical solar system comets, water is the primary driver of activity. You usually see a lot of water and a little bit of CO2. The ratio of CO2 to water in a normal comet is about 0.12. In 3I Atlas, that ratio is 7.6. Think about that. This comet has nearly 60 times more carbon dioxide relative to water than we expect. It is practically a dry ice bomb. Where did this excess come from? Maggiolo proposes a fascinating mechanism: galactic cosmic rays. For the billions of years that 3I Atlas drifted between the stars, it was constantly bombarded by high-energy particles from supernovae and active galactic nuclei. These particles slam into the comet's surface, penetrating meters deep into the ice. When they hit, they break chemical bonds. The model suggests that over billions of years, this radiation converts simple carbon monoxide and water ice into carbon dioxide and complex organic solids. It effectively creates a processed crust, a layer of radiation burned chemical slag that extends about 15 to 20 meters deep. Because 3I Atlas is so small, and because it is eroding fast, what we are seeing right now isn't the deep primordial interior of the comet. We are seeing this cooked crust sublimating away. 3I Atlas has, in effect, caught the mother of all tans, and now it's peeling. This finding implies that any object that has spent eons in the void will look like this. We may never see a truly pristine interstellar object until we catch one that is incredibly young, or until one breaks apart completely to reveal its unaltered core. 3I Atlas might have more CO2 than other comets, but that's not all it's been hiding. Josep Trigo Rodriguez and his colleagues compared the light spectrum of 3I Atlas to meteorites found on Earth. What they discovered was staggering. 3I Atlas's spectrum looks very similar to that of Cr carbonaceous chondrites, rare, primitive meteorites that contain tiny grains of iron and nickel material. So, 3I Atlas might well be carrying those metals too. In fact, reports from the UVES spectrograph at the VLT in Chile spotted nickel and iron in its coma back in September, with their data showing the comet to have a high nickel to iron ratio. This was unexpected. It's unlike any comet seen in our solar system before. Even 2I Borisov, another interstellar visitor we spotted in 2019. The VLT team noted that the nickel to iron ratio reduced as 3I Atlas approached the Sun, suggesting that Comet 3I could soon become indistinguishable from solar system comets in this respect. Why would it be important to find metals inside 3I Atlas? Well, when water ice melts inside the comet's porous crust, perhaps heated by the sun or by internal pressure, it comes into contact with these metal grains. In the presence of metal catalysts, water and carbon compounds can undergo what are called Fischer-Tropsch reactions. These are exothermic reactions. They release heat. This creates a feedback loop. The heat melts more ice, which reacts with more metal, releasing more heat. This in turn builds up pockets of intense pressure under the crust until the surface ruptures and a jet of gas and dust explodes outwards. This cryovolcanism could explain the surge in brightness, the jets, and the massive release of material. It also explains why the comet is rich in nickel and iron gas. So, where does 3I Atlas go from here? As of November 2025, the comet is emerging from the solar glare. It has survived its perihelion, though the intense mass loss has likely altered its surface forever. It is now outbound, racing away from the Sun and back toward the interstellar dark. But there's more to be had from this comet. As we publish this video, 3I Atlas will have just passed as close to Earth as it will ever get. And on the 16th of March 2026, the comet will pass about 0.35 astronomical units from the gas giant Jupiter. Models suggest this will be a remarkably close approach, passing inside Jupiter's Hill sphere, or the region where the planet's gravity dominates over the Sun. While it won't be captured, it's moving way too fast, Jupiter's gravity will tweak the trajectory of 3I Atlas one last time before it leaves the solar system. Crucially, this flyby offers a potential observation window for the Juno spacecraft, which is currently orbiting Jupiter. If Juno is still operational by then, we might get one final close-up look of this interstellar traveler from the perspective of the outer solar system. The story of 3I Atlas is far from over, but it has already taught us more in a few months than we learned in decades of theory about what's outside our solar system. It is revealed that the space between stars is not just an empty void, but a cosmic radiation oven that physically transforms the objects drifting through it. It has shown us that even small, fuzzy blobs can contain complex chemical engines capable of driving jets and surviving the inferno of the Sun. And while it may not be an alien spaceship, a rock that has traveled for billions of years, carrying the scars of its journey across the galaxy to tell us its story, is, in its own way, just as miraculous. Have you ever wanted to ask us a question? Our favorite section of the newsletter is dedicated entirely to questions and answers. Just sign up down below and reply to one of our editions with anything you've been wondering about. It can be about space, science, or even how we make our videos. We love hearing from readers and featuring your questions in future issues. It's a simple way to join the conversation and be part of the Astrum community. So, if curiosity ever strikes you, make sure you're on the list and ready to send in your first question.